Well, in this, our final video of Chapter 3 on free fall, it's perhaps time to finally explain this image and the images I've been showing. I hope you realize there's a strobe light, and the nice thing about a strobe light is it is at very regular time intervals developing the film. So when we look at our final photo, we can see superimposed on the film the positions that this dropped ball had at these equal time intervals. I hope you recognize that as being a motion diagram, because that's what we got. But what's really cool about this particular motion diagram is we have this backing of also equal distance intervals or equal displacement intervals. So we have a way of really gauging how this was moving. So I'm taking advantage of having those images and the displacement they had per time interval of the strobe light to draw on these displacement vectors. Now let's take a closer look. I'm going to get rid of the picture and focus on the vectors. And you can see that clearly each time interval the displacement is increasing. And we know by now that increasing displacement per time interval means increasing velocity per time interval. So it's a great way through this photograph and through the motion diagram displayed and now through these vectors to show you, make painfully clear that falling objects undergo accelerated motion. And with this image also used in an earlier video, we see the same phenomenon. Objects that are falling are objects that are accelerating. An object in free fall is undergoing a constant acceleration. Our challenge in the labs we've been doing, and now in this video, and the problems we'll be solving, is to identify what is that acceleration here on planet Earth and to apply it in solving these problems.
Hello, I am hoping to share with you a couple problems that we can do based on the ideas of the motion equations for constant acceleration. Keep in mind that free fall is a vertical direction only. The object is released or thrown, but in any case it is just simply along the vertical axis. All right, that means that we have one-dimensional motion, and we also know that the acceleration due to gravity, which is going to be a constant value of negative 9.80 meters per second squared, is going to allow us to insert that acceleration into any of the processes that we have with our free fall actions. When an object is in free fall, it is actually the state of an object that is acted upon only by the gravitational force of Earth. So there's no other forces, no drag, no friction. It is only due to the gravitational pull from the Earth. That means that we're going to generally use dense objects so that there is a very little implication of air resistance. All right? So what we're going to do is we're going to do a couple problems. Okay, these are the ones that I've picked out because they are going to give you an opportunity to apply the motion equations to free fall acceleration. Number 98 says that a stone is dropped and starts at rest in free fall for 8 seconds. So its initial velocity of the stone is 0 meters per second, and these are all in the vertical direction. It also says that it is in free fall for 8 seconds, so it tells us the time is 8.0 seconds. We know that the acceleration is due to gravity, and g is equal to negative 9.80 meters per second squared. And we are actually looking for two different things. Letter A tells us to calculate the stone's velocity after 8 seconds. So we're going to start with that first. That would be the final velocity. So let's consider what this tells us. What it tells us is that we need the motion equation that does not have displacement. Literally, we're going to work with the first motion equation, v final equals v initial plus the acceleration times the time. Notice that it's dropped from rest, so our initial velocity is going to be 0 and can be crossed out. Now we have the final velocity as just simply the acceleration due to gravity, which we can rewrite as little g, times the time. I go then to my calculator and I can just simply put in negative 9.80 meters per second squared times the time of 8 seconds. And that gives me a final velocity. On my calculator, I see negative 78.4. And I glance through and I see two significant figures. So I'm going to keep it in two significant figures. So it's going to be a negative 78 meters per second. And that is the downward final velocity. Negative 78 meters per second. All right, now let's go to the second part of number 98. And in that one, they want to know, letter B, how far does it fall? That's the question. What is the stone's displacement during that time? So now we're looking at the displacement in the y direction. We still know that the acceleration is due to g, negative 9.80 meters per second squared. And they want us to stick with the same amount of time. What is the stone's displacement during this time? So I'm going to stick with the 8.0 seconds. And I am also going to work with the fact that it was dropped from rest. So the V initial is 0. What I don't want to use is what I just found in letter A in case I'm wrong. It's always good to go about it in a fresh way. So now I'm looking at these different values and I see that what is not present is V final. So what I can do is use my third motion equation that the displacement is equal to VIT plus 1/2 AT squared, and I'm just going to write in G for my acceleration because I know what the value is. So what I'm going to do now is just simply solve, because it's already algebraically transformed for D. To find that out, I'm going to realize that my initial velocity is still 0. So that first term, 0 times time, is going to be 0. And I'm going to multiply on my calculator 1/2, which is 0.5, times negative 9.80 meters per second squared times the total time squared, which is 8 squared. And that is going to give me a number on my calculator that says negative 313.6 meters. I look at my significant figures, and again, I'm limited by this 2 significant figure time. So I'm going to say that the displacement is 310, and it's going to be negative because that's how my calculations came out, downward 310 meters. And that is the second answer in question number 98. Okay? Question 99, I'm reading, says a bag is dropped from a hovering helicopter. So, if we're looking at number 99, we want to understand that dropped means that its initial velocity is 0. So that's what we're going to take a look at. The initial velocity is 0 because it's dropped from rest. It's dropped from a hovering helicopter. The bag has fallen for 2 seconds. That's our time. 2 seconds. And we're looking at what is the bag's velocity. Okay, that's part A. What is the bag's velocity after that time? So that's the final velocity. Here, we also want to recognize that we are going to be using the acceleration due to gravity. So sometimes you forget about that and then you think, oh wait, I do have that. I know that it's falling, and so it is in a gravitational acceleration. So we're going to write that value as negative 9.80 meters per second squared. So now, again, I have initial, final, time, and acceleration. And so what I can use is my first motion equation. V final, which I'm looking for, is equal to V initial plus the acceleration, which I'm going to call G here, times the time. And I can just very easily go into my calculator. I recognize that, again, it was dropped from rest, so that 0 initial velocity doesn't need to be put in. But I'm going to put in my acceleration due to gravity. Downward is negative 9.80 meters per second squared times the time, which is 2 seconds. And I'm going to have a final velocity of negative 19.6 meters per second on my calculator. Now, what I also want to realize is two significant figures will give me then an answer of negative 20 with a dot meters per second. And the negative just simply means downward. Okay? There is a second part to this problem, though. So let's take a look at 99B. It says, how far has the bag fallen during that time? So now I'm looking for my displacement. Okay, these are all in the y direction. All right, and again, I have my initial velocity of 0. I've got my time the same as 2.0 seconds. And I'm not going to use my final velocity because there might be a problem with that, but I do know that the acceleration is due to gravity at negative 9.80 meters per second squared. So I choose my motion equation based on displacement, initial velocity, time, and acceleration. So I can work with the third motion equation. The displacement is the initial velocity times the time plus 1/2 the acceleration, in this case it's g, times t squared. I can solve directly because I already have it isolated on the left, and I can understand again the initial velocity was 0, which 0 times anything is going to take out that entire term. And then I'm going to put in 0.5, that's 1/2, times negative 9.8. You can't forget your negative 9.80. And then I'm going to realize the time is 2 seconds, and I'm going to square it. And that is going to give me a displacement downward, and it comes out negative, of negative 19.6 meters downward. Looking at my significant figures, I see two significant figures, and so I report this as d is equal to negative 20 with a dot meters downward.